Thank you, everybody. Welcome to the conference. I hope you have a great few days. So, I just need to change over my the slide deck, excuse me. This one. Right, so I want to be talking about software engineering. And I've been kind of talking about software engineering for a few years now, but sort of by accident. And what I mean when I'm when this kind of came to my mind is that I think that in certain circles of the software development community, the term software engineering has got something of a bad name. And I can understand the reasons for that, but I think it's kind of unfortunate. I think it tends to conjure up pictures like this. And we tend to think of software engineering in terms of big upfront design, heavyweight plans and all of these sorts of things. And I have nothing against diagrams. I don't even have anything against UML. I think it's a useful tool sometimes. But this is as close to software engineering as a soldering iron is as close to electrical engineering. They're not the same thing. And so this is not software engineering. So we sometimes talk about process, and we think about the importance of process. And I'm a big believer in the importance of process. I think it's an important tool as well. But this isn't software engineering either. Anybody, any idea how many times the Scrum documentation mentions the word code or software? Any idea? I'll tell you, none. So it's useful, it's helpful, but it's as opposite for planning plumbing as it is for planning software development. So we need something that's useful for our stuff as well. In recent years, there's been a movement towards craftsmanship, and I think there are some good reasons for that, which I will explain why I think that happened. But I don't think that this is what we're talking about either. Craftsmanship is important. I think taking pride in one's work and doing a good job is important, but I don't think it's sufficient to our needs. So let's take a little bit of a look of the kind of history of production, because I think that informs thinking about processes at least. And for much of human history, everything that we created was as a result of kind of craft-based processes. And then 150 odd years ago, we kind of came to the ideas of standardization of components and mass production. And then at the end of the Second World War, we started applying more kind of scientific rationalism to the processes, and lean engineering and lean production techniques flowed from that. So let's look at a little bit more detail about what we're talking about with these things. So craft-based production is kind of much more art than it is science. There are no work standards. It's really down to the individual skills of the person undertaking the work. Each piece of work is individually crafted and unique in that sense. And to be frank, on the whole, despite our somewhat romantic vision of handmade things, it's low quality compared to production engineering. Just for a moment, if you don't believe me, just for a moment, think about a hand-built iPhone. It doesn't make an awful lot of sense. Mass production came along. Mass production actually started before the Ford production line. Ford was the first assembly line, but one of the things with mass production was the American Civil War. That was one of the first places where mass production techniques were used to build arms. And there's a sad as that is, there's an interesting story. There's the man that was trying to get the contract for supplying arms to the northern states went to Congress and he got a bag of components. And he tipped the components onto the floor, and he got the congressman to pick out individual components from the pile, and then he assembled a rifle from all of those pieces. That's the first time in history that was possible, because that was the first time that there was such standardization of parts to make that possible. Before then, every gun was handcrafted from beginning, and to the extent that people would actually mold their own bullets to fit their gun. So mass production is about assembly lines, it's about standardization of components, standardized steps, piece-based metrics, measuring the efficiency of the process by how many components you create, and so on. And then at the end of the Second World War, Deming went to Japan and introduced the Japanese to the ideas of kind of a more scientific approach to production engineering, really, and process. And out of that came, over many iterations and the Toyota process and all this kind of stuff, came the ideas of lean production, which in many parts of the production world, is overtaking the production techniques of the more advanced organizations. And so what's that about? That's about putting quality at source, making sure that the things that we build are very high quality. We want pull-based systems, and from that idea of pulling things instead. So if you think of mass production, it's kind of pushing things down the line. You make lots of components and you're pushing things towards the end goal. And with pull-based systems, you're kind of saying, I just want things just in time. I'm just going to pull these forwards and just have these components to work on. And that's where sort of just-in-time delivery, just-in-time warehousing, all those sorts of things, those come from that kind of idea. We want to minimize the amount of work in process. We want to be working on things through to completion and minimize the waste in the process. And ideas like one-piece flow all kind of play in this space. The other kind of interesting take on this, I think, is if you look at chemical engineering, one of the aspects of chemical engineering is that by definition kind of thing, by the nature of their jobs, chemical engineers are experts in process because that's what they do. They create industrialized processes to deliver different kinds of products. And so they have a taxonomy for process control methods. And this is one of the process control methods that they identify, the defined process model. So defined process control model requires that every piece of work should be completely understood, given a well-defined set of inputs. The same outputs are generated every time. A defined process can be started and allowed to run until completion with the same results every time. That's fine. That's useful for some kinds of things. If you're building rifles or if you're building cars on an assembly line, maybe that works out. This is the world, this is the kind of process where these techniques work quite well. So mass production, assembly lines, waterfall style processes where you're being predictive. Unfortunately, I think that bears no relationship to any software project that I've ever seen in my life. This is another one of their process control models. This is the empirical process control model. The empirical model of process control provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. That sounds an awful lot more like software development to me. And this is the space where craft-based production techniques, exploration, continual improvement, and lean process play. So I think this is one of the reasons why craft-based software craftsmanship has gained some currency. It is an approach that works in this problem domain. Unfortunately, I don't think it's unless you are lucky and you have a master craft, all of your team are composed of master craftsmen, it's not an approach that scales particularly well, and it's not an approach that produces really, really top quality work. Unless you've got the kind of the people that that great software flows from their fingers, and those are very rare people. On the whole, my point is, if you were flying in an aeroplane, would you prefer that the aeroplane was built by engineers, or would you prefer that the aeroplane was built by craftsmen? I prefer the engineering approach, personally. And our problem domain is such, we are, strange as it may seem, we are the people that are changing the world. We are the people that are reinventing what our high-tech society is, and some of the things that we are building, people's lives depend upon it. I'm working with several of my clients that build machinery and software in the healthcare industries, and if they get the answers wrong, they can kill people. Part of my background is in finance, where there'd be billions of pounds worth of other people's monies flowing through the system. These things are serious, and so we need to consider that. So where are we in the software industry? I think we're not mass production, and I think we never will be. It's completely the wrong model. We're never, ever going to be assembling pieces from components from Lego bricks and assembling, because if we could, and assembling systems out of that, because if we could do that, there's no design, there's no need to be developing software in the first place, because we've already developed it, pretty much. So that's not where we are or where we should be aiming. I think that this is where we are. I think we are working in a craft-based environment on the whole, and I think that this is where we should be shooting for. I think this is where we should be targeting. One of the reasons why I think this is important is because the history of software project success. If software projects were normal things, there ought to be a normal distribution of software project success. as many software projects ought to finish ahead of schedule, under budget, delighting their users, as finish behind schedule, over budget, and pissing off their users. But I don't think that's the picture that, on the whole, we recognise as normal for our industry. I think that the normal curve for our industry looks more like that. And that has serious implications in terms of the way in which we undertake software development, the way in which we create teams to develop our products, the way in which we fund it, the way in which we plan it, the way in which we undertake the design, the development, the release into production. All of those things are impacted by us being scared of the failures that are so common in our industry. I actually think it's telling us something else. I came across this beautiful little GIF animation a year or two ago, and it just resonated with me. This is two different views of the orbits of the planets and the sun in the solar system. And on the right-hand side is the geocentric view of the solar system. This was the model that was held by humanity for thousands of years, and that assumed that the Earth was at the center of the solar system, actually the center of the universe, and that everything rotated around the Earth. And if you plot the movements of the sun is fine, the sun goes around us, but the planets, they don't look quite right. They do all of these weird things. And some of the most complicated machinery that was ever created up to this point in history, while this was the kind of prevalent viewpoint, was to try and figure out where the planets were in the skies. They had complex clockwork machines to determine where the planets would go. If you've got this kind of model, because it's the wrong model, you add complexity. You get more and more complicated to explain all of the weird things that just look weird. Sometime later, Copernicus came along and said, no, we've got it wrong. It's the sun that's at the center of the solar system. And if we assume that that's correct, then the model looks an awful lot more simple. It's an awful lot easier to make predictions from this kind of model. Even I can do the maths for this model. And so, in this world, Newton can come along and come up with an inverse square law. A few centuries later, Einstein can come along with bendy sheets of space-time and general relativity. Those are not predictions that flow from this model. So having the right model for what it is that we're doing is really important. And I think that on the whole, the software industry is in the sense that we're working in a geocentric view of what it is that we're trying to achieve. Now, for some reason, which I can't fathom, this is a lovely picture, isn't it? This is the picture that we chose for the front of my book, but it's a beautiful picture. For some reason, I can't work out, whenever we end up talking about engineering, people start talking about building bridges. And software engineering is nothing like building bridges. It's different. But even so, when we talk about building bridges, we tend to talk about a fairly naive view of building bridges. If you're building a brand new bridge, a kind of bridge that nobody's ever built before, then you're going to be experimenting. You're going to be building models. You're going to be doing stress tests. You're going to be doing all sorts of iterative little trials to figure out what goes on. You're not just going to have a big Gantt chart and plan for all of the materials to arrive on the first day and then figure out what you're going to do. That's not the way it works. Between different engineering disciplines, engineering is not the same stuff. Building a house is not the same as building a bridge. Chemical engineering is an entirely different discipline. Aerospace engineering, automotive engineering, electrical engineering, all of these things approach engineering from a different perspective. So that tells us something about our engineering. Software engineering will be different to every other kind of engineering. It will be our own thing, and it should be our own thing. It's different on scale as well. These two structures are both engineered structures. You can bet if this is an IKEA shed, that they've done some analysis to figure out what's the minimum amount of wood that they could build the shed out of. On the other hand, this is the tallest building in the world, and the engineering that went into that is going to be leading edge. They're going to be doing finite element analysis, again, building models and structures and working out the aerodynamics of the building and all this kind of stuff. So engineering's different. If I'm writing software that's running the flight control system on a passenger jet, the level of engineering that I should be employing is probably different to if I'm writing software to run my mother's cake shop. But nevertheless, we're probably going to benefit from some level of engineering kind of discipline, engineering thought to apply to that. So what is engineering? I've been talking kind of around the edge of this topic for a couple of years now, and occasionally I've tweeted things and stuff like this, and this is one of the replies that I got from somebody. I've redacted their name because I really strongly disagree with this, but and I don't want to be pointing fingers at anybody, but this person sent me, for me, engineering means working in a certified, inflexible process that includes planning ahead a lot, the antithesis of agile. I think that's mistaking what engineering is. Engineering is a process of discovery. It's a process of learning and adapting. The stuff that he's talking about is production. Is once you've solved all the problems, you just create the things. Production for us is the push button. It's the automation, the compilation. It's that stage. So that's not the interesting part. It's the design. It's the solving of the problems that's the interesting part. So I don't think this is even close to understanding what it is when we're talking about engineering. So let's look at some definitions, and I'm not going to read all of these out in detail. This is the Wikipedia version, and I think there are some interesting words in here that we're going to pick on, some themes. So it's about empirical evidence, scientific, practical knowledge. It allows us to invent and design and maintain research and all these sorts of things. Here's another definition. So the art or science of making practical applications of the knowledge of the pure sciences, and here's another one. The application of scientific and mathematical principles to practical ends. So this is my working definition. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. I think that that's what we should be doing. I think that that's what, as software development, we should be trying to achieve. There's a lot, having said all of the differences between different kinds of engineering, there are also a lot of similarities. There are lessons that we can learn. One of the things that's interesting is that the Shard, not a couple of miles away from here, was the first building to be built using iterative principles. They built it down as well as up at the same rate. Normally, the normal practice for creating a building like that is to build all of the foundations that are necessary to support the massive structure that you plan to build, and then you build the massive structure. That's not how they built the Shard. They built it incrementally, developing enough to support the first few tiers of the building, and then they went down further, and they were building down and up at the same time. Interesting stuff. So these are the principles that I think are fundamental to, I think probably any form of engineering, but certainly to software engineering. I think these are the things that we should be thinking about applying in our work every day, at every resolution of detail. This is kind of fractal. This is true at the smallest level and at the biggest level. So let's walk a little bit through these definitions and figure out where we stand on each of these things. So we want to be iterative. We want to be able to repeat the process and use that to approach the desired goal or target of what we're trying to achieve. Iteration matters because it allows us to learn, react, and adapt to what we see. It gives us an opportunity to steer the course of what we're doing. And if we're on the wrong course, to change course. One of the things that I talk about in training courses and this sort of stuff is nobody knows what the destination is, what we ought to be doing. So we want to plant kind of a vague destination. We want to say, Elon Musk, let's let people live on Mars. How do we let people live on Mars? I don't know. Figure it out. And then you do lots and lots of little experiments. Oh, well, one of the things we'll need is reusable rockets to make it economical. So we'll have to figure out how to make them land. And all of these ideas kind of flow if we start thinking about these terms and being iterative and allowing us to evolve the solution to complicated problems. It allows us to steer towards a goal. It allows us to have that flag planted on a hill somewhere, the purpose that we're striving for. And it allows us to carry out a series of small experiments and navigate. And sometimes we're going to go in the wrong direction, but that's fine. We're going to learn lots when we go in the wrong direction. And it allows us to apply continual improvement. By doing things over and over again, we're going to be able to refine them. We're going to be able to improve them. We're going to be able to make them better and better over time. the practice that an iterative approach gives us allows us to really take this improvement seriously. And I think this is one of the big wins of continuous delivery and most iterative agile processes that they give you, is that you're practicing all of the disciplines that are required for software development every week, every few days, whatever it is. And so you're refining the techniques, you're highlighting the bits that don't work so well, and you're figuring out how to improve those things. Feedback. Feedback is information about actions returned to the source of the actions. I think feedback is absolutely fundamental to any good software development process and any engineering approach. We have to get feedback to understand the impact of our choices. We have to establish the way in which we work to be able to learn and adapt and get the benefits of our iterative processes. If we're not collecting the feedback, we're just going forwards quickly and we're not learning. So it means that we can observe the impact of our choices and we can understand whether they're good or bad. There's data from the industry that says the best companies in the world, 2/3 of their ideas create zero or negative value for the companies that undertake them. If that's the world in which we live, and I assure you that it is, then the only sensible thing for us to do is to optimize, to have lots of ideas, try them out as cost effectively as we can, and discard the bad ones as quickly as we can, because most of them will be bad ideas. That's not a critique of us. It's just who we are. It's just who we are as a species. It's just the way in which we work. We're not great predictors of the future. This is my model. I use this model all of the time when I'm talking about continuous delivery. It's a little bit oversimplistic, but it kind of gives the outlook. For me, continuous delivery is about optimizing the development process from having an idea to getting that idea into the hands of users and figuring out what they make of it. So that's part one of the feedback loop. In order to achieve that, you need this really tight feedback loop in the middle. You need to be able to do probably test-driven development to create lots and lots of unit tests, get feedback on the fine-grained changes to my code base. And then in between that, we want to evaluate whether the changes that we're making are functionally correct and do they do what we intend in terms of delivering the value to the users. And so we'll use ideas like executable specifications and that feedback loop to drive the behavior as well. We want to work in incremental ways. As well as being iterative, we want to be incremental. So what's that about? Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application in which components can be freely substituted if somebody improved and can ensure better performance. So we'd like to get to those sorts of ends. I think that this is one of the driving ideas sort of behind the techniques like microservices and so on. It allows us that ability to be more incremental. But whatever the nature of our software or software architecture, it's a desirable property to be able to change things. Modular systems has an interesting history in terms of other forms of engineering. This is the Saturn V-B, the Apollo spaceship. This is the most powerful rocket that we've created so far. Elon Musk is planning to build bigger ones, but this is the biggest so far. And this was interesting because one of the ways in which they solved the problem of going to the moon was to create modular systems. So this module got the spacecraft from Earth into Earth orbit. You can see that's a big problem because you've got to lift the payload and get up to 18,000 miles an hour to get into escape velocity to get it into Earth orbit, and that takes an awful lot of energy. These modules, so the conical bit at the front is called the command module, and that was dedicated to getting the 3 astronauts from Earth orbit back to the ground. And then the cylindrical bit at the back was this service module, and that was designed to get the astronauts from the Earth to the moon and back again. And then there's another bit that I haven't got a picture of here, which was the lunar module, which was itself in 2 pieces. There was the descent stage, which allowed them to land on the moon, and the ascent stage, which brought the 2 astronauts back up to rendezvous with the guy in the command module and the service module in lunar orbit. So this was a modular system, and they hadn't had this picture at first. If you look at pictures of lunar exploration from the 1950s, they had a big space rocket, a kid's space rocket that took off from the Earth, flew to the moon and landed on the moon and then flew back. Too expensive, doesn't work like that. Modularity is an important idea, and we should be able to apply that. It's doubly important in our sphere, I think. Modularity is important for another reason. It allows us to focus on quality. So one of the techniques, agile techniques in general, continuous delivery specifically, is about using small batch sizes. We'd like to release many small, simple changes rather than fewer, big, complicated changes. And that has an impact on risk. So what do I mean by that? So if you think about a large change with lots of changes in it, and how do we work out what the risk of that? There's going to be a risk of some changes. So the total risk is going to be the sum of all of the changes. We're going to add all of the changes together, and if we've got a large batch of changes, we're going to have lots of changes added together. But there's another part to the risk of a release of software into production. In addition to that, we've got the risk of changes interacting with one another. Changes, if I release multiple changes, then maybe they might interact in a bad way and cause a problem that I hadn't anticipated. And so that's an exponential. So in this equation, n is an important number. The number of changes is important. So let's look at that. So if we're making few large changes, this is what most of the world of software development does, then lots and lots of changes in there. So what's the risk there? So n is very large, which means that the risk is high because of the formula. And then if we decompose that into many, many small changes, ideally trivially small, ideally a few lines at a time, ideally I'm committing after every test-driven development unit test passes, and that's in a position at least to be released into production. So if we do that, n is very small, and so the risk is low. This is reinforced from data from the industry. If you look at the failure rates, Amazon are one of the classic examples of this. Amazon released change into production once every 11.6 seconds, and since they've been doing that, they've seen a dramatic reduction in the failure rates. There's a direct correlation with this. So, iterative and incremental, they sound very similar. So what is it that we're talking about when we're talking about this? This is a beautiful little visual demonstration that I stole from Jeff Patton. So iterative is about doing something, and the scaling factor is kind of the level of resolution, the level of detail. So the first release of my picture is a sketch. And then I might refine the sketch and make it a little bit different. I've changed my mind a little bit about where the hands are, and then I'm going to fill in some detail. And then ultimately I get to the end result by trying things out. Incremental is different. Incremental is about doing things stepwise and componentizing and breaking it down into different chunks. Both of these have a role to play. So on the face of it, often we'll talk about iterative being the kind of driving force between agile processes, and it is. But being incremental is important too. Identifying the things that we can get away with and not releasing yet, but still getting to some value is important and useful. We want to be experimental. One of my nerdisms is I'm interested in popular science. I'm a kind of physics junkie, and I believe I see stuff from that position. I see stuff from that sense. I believe that the reason why these more effective development practices that we're talking about work is because they are the application of the scientific method to software development. That aligns quite nicely with my idea of what engineering is, which, you know, that might be just my personal prejudices. So what's experiment? An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. Well, that sounds like a nice idea. It's not how most of us do software development, but it'd be nice if we did. One of my other nerdisms is I'm interested in aerospace, and you saw from earlier the space program and the Apollo space program in particular. And so I want to tell you a little story just to kind of illustrate my point about being experimental. So in 1961, JFK, President of the United States, stood up in Congress and said, we're going to send a man to the moon by the end of the decade, and we're going to bring them back. And everybody at NASA at this moment went, because they had no clue how to do this. This was about 2 weeks after Alan Shepard, who was the first American in space, did his suborbital lob. So they strapped him on top of an intercontinental ballistic missile, launched him 100 miles up, and he parachuted back down. He didn't go into orbit. That was the first American in space. And this was 2 weeks after that. Alan Shepard was an enormously brave man because at this point, all of these missiles were blowing up on the pad. They hadn't got the launch right even yet. So at this point, Kennedy's saying, we're going to the moon. It's, interestingly, probably the biggest story that anybody's ever, biggest agile story that anybody's ever suggested. And so he's painted this vision. He's painted this vision of where people are going to go. We'd like to go there. Here's my hill. Here's the flag that I've planted. I'm a president. I have no clue how to do this. But all you techie people, you sort this out. So where do you start? Where do you even begin with this kind of problem? Here's a series of things that they didn't know how to do, which is pretty much all of the things that you need to know how to do. So they weren't launching spaceships successfully. They didn't know to launch. They hadn't yet had the idea of modular systems. They hadn't yet had the idea of breaking the spacecraft down into different components. They were still thinking of one spaceship going all the way, pretty much. They hadn't done any multi-stage stuff yet. They hadn't got re-entry really sorted yet. Shepard had done it in the suborbital lob, but they hadn't done it. They hadn't got spacesuits right. There'd been pressure suits since the 1930s, but they hadn't got spacesuits that people could walk about on a planet, on another planet with. They hadn't got no human beings. They'd yet docked two spacecraft together. No human beings had done a spacewalk. So all of these things were kind of, what do we do now? So where do you start when you've got a challenge on this kind of scale? So you try and break it down into small steps. So here's a picture of the Earth-Moon system. This is not a picture of the Earth-Moon system. This is a kid's storybook picture of the Earth-Moon system. This is a picture of the Earth-Moon system to scale. And at this point in human history, no human artifact had been more than 1 pixel away from the planet Earth. So problem 1, how do you get all the way over there? You can kind of imagine the conversation going on inside NASA the next day after Kennedy's speech. How are we going to do this? Well, I don't know. We could put the astronauts in the spaceship, send it to the moon, and see if they come back. Yeah, well, that's probably not the best way to retain our funding. It's probably not really how we're going to keep going for many. Okay, so that's not our simplest experiment. We could just send the spaceship. We could send an automated spaceship to the moon, bring it back, and then we'd know where they're working. Well, that's great. We're probably not going to kill all of our astronauts, and we're going to retain funding for next year, so we'll have more experiments. So that's a step forward, but it's still way more complicated than we could do. Well, bringing it back is really complicated. There's a whole lot of stuff that you have to get right to bring it back. Why don't we just send the spaceship to the moon and land it on the moon? Okay, well that cuts out a whole raft of problems, so that's good. We'd learn stuff from that. That's a great idea. What does landing on the moon mean? Well, it doesn't have to survive the landing on the moon. So that's where this came in. This is the Ranger program. This program was literally spaceships as bullets fired at the moon to see if they could hit it. So how did this go? The first launch, it blew up on the pad. We could have predicted that, couldn't we? The second launch, it blew up on the pad. The first two were aimed, the first one at least, was aimed at getting the spaceship just into Earth orbit. Didn't make it. The second one, they aimed at getting the spaceship into Earth orbit. Didn't make it. The third one, this will make you laugh. What do you do when your project's behind schedule? Push on. So the third one, we're not just going to go for Earth orbit this time. We're going to go all the way to the moon. So it got into Earth orbit. It worked. They got the launch. They got it into orbit. They did the deorbit burn. They fired it off towards the moon and missed. The fourth one, into orbit, did the deorbit burn, all of the systems packed up. Almost immediately, they got no data whatsoever, but they managed to track it from ground-based radar, and they saw it hit the moon. Sorry, ground-based telescopes. The fifth one, missed again. The sixth one, it impacted, but the cameras failed, so they got telemetry, but no pictures. So they're getting closer. It's starting to work. The seventh one worked. The eighth one worked. The ninth one worked. So when you're NASA and in the middle of the Cold War, you're the most important thing that's going on in the Cold War as far as the Americans are concerned. You've got essentially an unlimited budget. You've got access to the finest technical engineering minds on the planet. How do you approach this kind of problem? You approach it by carrying out experiments. You don't have a big Gantt chart and plan it out all ahead. You figure out what's the smallest step that I can take. In this case, the small steps were quite large, but no doubt there were many smaller steps. Each component of this thing would have been experimented on and tested and evaluated in small contexts as well. There's an awful lot of detail behind this, but nevertheless, it's an experimental technique. And this is the only way in which we solve hard problems. It's not just the best way, it's the only way that we solve really hard problems, I would argue. So being experimental, though, is not obvious. It's not necessarily a slam dunk. Has everybody seen this kind of thing before? Yes? So this is one of those kind of tests. You're supposed to say, which dot is bigger, which orange dot is larger, the one on the right or the one on the left? Could I have a show of hands for people that think that the orange dot on the left is the biggest? Show of hands? Nobody. Who thinks the one on the right is the biggest? A few people. And who thinks that they're both the same? Okay, so how would we find that out? Well, we could do an experiment. There's an experiment. We've had a look. They're both the same. It's an optical illusion. Cool. Have people seen this one before? Yes? So this is a similar thing. Which line is the longest? So who thinks that the line on the left is the longest? Nobody. Who thinks the line on the right is the longest? A few people. Who thinks that they're both the same? Yeah, were you listening? You have to carry out the experiment. I was lying. I made the one on the right longer. We don't know. We can't tell until we do the experiment. We need to measure. We need to understand what's really going on. Anything else is just guesswork. We want to work empirically. I think one of the things that's interesting about our discipline is that it often appeals to the same kinds of people that are interested in mathematics. And so we tend to think a lot about maths. And I like maths. I think maths is a good thing. It's interesting. It's beautiful, but it's a tool. And I'm neither of these things. But if I was a choice between a mathematician or a physicist, I'm a physicist. And physics is more about the practical application, the understanding the application of maths to solving problems. And ultimately, I'm kind of an old school science physicist kind of shaped person. I think you've got to get to experiment. I think all of these things about multiverses are lovely theories. Where's the experiments? We've got to get, that's real science. And so being empirical is important. Being theoretical is great. It's lovely to be able to come up with a theory and use ideas like maths and stuff to push us forwards. And then we've got to measure it against the real world because our theories might be wrong, our models might be wrong. So being empirical, I think, is really important. Verifiable by observation rather than theory or pure logic. When we do this, it means that we can be evidence-based. We can capture evidence. We can separate out the things that we're guessing at, the myths, from the truths. And we can understand how to move forwards on this basis. So here's our model for engineering in the context of software development. So it needs to be iterative, it needs to employ feedback, it needs to be incremental, experimental, and empirical. So where does this stand in terms of continuous delivery as an engineering discipline? I'm big-headed, but I think it ticks all the boxes. It's absolutely an iterative process. It's defined to be working through in these cycles, these fast cycles, to let us learn and adapt as quickly as we can. The deployment pipeline is this wonderful mechanism that allows us to see the impacts of our changes and understand what those are. It consciously focuses on the delivery of feedback at all stages. we look to for ideas like cycle time to reduce how long it takes us to get answers back to the changes that we make, to get feedback on on our ideas and understand their impact. It's incremental. We're going to build stuff up piece by piece over time. We're going to use iterative techniques to build just enough to get out into production as early as we can to learn, and then we're going to incrementally add more and more behaviors to the system over time and learn more that way. The deployment pipeline itself, if we're building a deployment pipeline, we're not going to build the massive engine before we do anything else. We're going to build a little bit. We're going to try it out and see how that works, and then we're going to refine it. We're going to adapt it. We're going to grow it. It's experimental. Again, the deployment pipeline allows us to carry out experiments inside the organization. The feedback that we get from customers, the ability to deliver software reliably and efficiently into production allows us to get feedback from our users and understand the impacts of our ideas with our users. And it's empirical. We're basing our decisions on data. We're collecting information. We're using the deployment pipeline again as a falsification mechanism. We're using data from production to understand what our users make of our software, and we're making choices based on that information. So I think that there's a fair shout that what we're talking about here is a genuine engineering discipline. I think that continuous delivery is not unique in this. Continuous delivery is the son or the grandson of extreme programming. It's these same ideas extended somewhat further in the reach of software development in some ways, somewhat refined, but it's the same idea. And there was, I apologize to the man because I've forgotten his name at this moment, but one of the founders of Scrum said that he'd never seen a successful Scrum project that didn't have aspects of extreme programming at its fundamental engineering core. We need to take the engineering part of software development seriously. We are building complex systems. Even when we're building software for my mum's cake shop, we're still building complex systems. And so we need to be able to work in ways that allow us to verify the nature of our work. We need to take automated testing seriously. We need to take deployment automation seriously, all of these things. And when we do that, we become more efficient. We become more effective. We start living in the heliocentric solar system rather than the geocentric solar system. We remove complexity from our development process. So, I think that the model of continuous delivery is really important in being able to apply these kind of engineering disciplines. At its root, I think it's about this. And this is kind of really what science is about. So we're going to make an observation of some kind. We're going to propose a theory, and we're going to make a prediction based on that theory, and then we're going to create an experiment to test the prediction, and that's going to change our observations, and we're going to go round that loop and round that loop. And again, this is fractal. This happens at all levels of resolution. This is just as true at the level of the individual unit test case that I am creating as I'm doing test-driven development, as it is when I've got a business idea and I'm trying to figure out what the minimum viable product is to get something out into the hands of users to figure out whether the users are going to like this idea or not. These are the same techniques. So, if we want to apply these kinds of techniques, we're going to be able to design stuff, we're going to be able to develop stuff, we're going to be able to test stuff, we're going to be able to release stuff. And if we take this stuff seriously, we want to be able to do this all of the time. We're going to be doing this continually. These are not stages, these are not phases, these are activities that happen all of the time. And we're going to iterate and increment through this process to make this happen. We're going to have fast cycles that allow us to try these different things and figure out what works. Again, at all resolution, at the level of my design, scalability, performance, all of those things, but also at the level of what do my users make of the change. This is the cycle time. That's an important driving factor. The idea of a cycle time is how does it take you? How does it take you to go through the normal cycle? How long would it take you to make the simplest change that you can imagine to your production system, go through all of the normal steps and push that into production? And driving for shorter cycle times is the surest way that I know of improving your development process, using experimental, empirical, iterative techniques to achieve that. And what this allows, if we have an engine, a process, machinery, discipline focused on this kind of thing, what this allows is it allows us to carry out these theories, predictions, experiments, observations in different places at different parts of the process. Not just all the way to production, but also inside the process, using our automated tests as forms of experiments and opportunities to learn and adapt from there. And that's a pretty good diagram of what continuous delivery is about. So I think that continuous delivery, I am delighted how popular the idea of continuous delivery has become. I make a good living going and talking to people about continuous delivery. It's a pleasure to me that the book that Jez and I wrote together is popular, but I think it's more important than that. And I don't, if we could get to an engineering discipline for software development and it wasn't called continuous delivery, I would be the first person to be praising whoever achieved that, to delight that. So this is something of a call to arms. This is start thinking, let's take back software engineering as an idea. The people that are drawing those Gantt charts and those UML diagrams and provable methods, I'm sorry, but that's not engineering. Those are tools that you might use to achieve some engineering. We are the engineers. We are the people that are being iterative, incremental, experimental, using feedback. We are the engineers. That's the end of my talk. This is a new talk, and so it's slightly shorter than I anticipated. So that's good, because it means that we've got lots of time for questions if there are any. Thank you.